Okay, so we are being recorded. We're being recorded. Okay, so last time we talked about using row operations to reduce a system of linear equations into reduced echelon form. And the row operations that we used were part of a row reduction procedure that's actually outlined in section 1.2. So we were essentially covering section 1.2 at the same time. In section 1.2, they go through an example 3, where they take an augmented matrix. Well, it's actually a matrix, and they get it in reduced echelon form. So you know, you've already seen that done. But what I want to do is bring up something from the book here. Okay, so section 1.2 gives a formal definition of echelon form in reduced echelon form. And it's at the top of page 13. And following this, this definition, you see echelon form, there are 3 criteria that need to be satisfied. And then to get the matrix in reduced echelon form, you need all these 5 criteria to be satisfied. And I think it's helpful to look at an example here. In example 1, example 1, hold on here, let me highlight this. The following matrices are in echelon form. So echelon form, first of all non-zero rows are above any rows of all zeros. And that's true in these 2 matrices here in example 1. So I'm focused on those 2 matrices there. It says also echelon form, each leading entry of a row is in the column to the right of the leading entry of the row above it. And that's true. Okay, so when you get the matrix in triangular form, this naturally happens. And then the third criteria for a matrix being in echelon form is that all entries in a column below a leading entry are zeros. So the black dots represent leading entries. Okay, and you can see below the black dots, which are the leading entries for each row, you see zeros below the black dots, the numbers that would be in the black dots. All right, so are there any questions about those 2 highlighted matrices? All right, and it's important, you know, when you get to these conceptual questions, this is where you have to be comfortable with the definition. But I always like to look at examples that helps me a lot with the definitions. Now, if we continue in example 1, it says the following matrices are in reduced echelon form. Okay, reduced echelon form, then there are 2 more criteria. The leading entry in each non-zero row has to be a 1. Okay, that is necessary for a reduced echelon form. And you can see that's true with these 2 matrices. And additionally, each leading one is the only non-zero entry in its column. Okay, and that's very true. That's very true. Wherever you have a leading entry of a 1, that column, the rest of the column contains zeros, and that's true. Okay, so are there any questions so far with the difference between echelon forms and reduced echelon forms? All right, maybe give me a few thumbs up if you're comfortable, and then we'll move on if you're okay. Thank you, everybody. Thank you. So, if you get the matrix in echelon form, you can use back substitution to figure out like if you have an augmented matrix and you get it in echelon form, you can use back substitution to figure out the remaining values. Okay. In other words, you would be echelon form means you're doing the forward phase of the reduction algorithm, but not the backward phase. But for reduced echelon form, you're doing a forward and backward phase. And that's actually very desirable because reduced echelon form, here's one of the things about reduced echelon form. Every matrix is row equivalent to one and only one reduced echelon matrix. So like for instance, if each of you are solving a matrix, you're solving an augmented matrix, and you do row operations and you get the matrix in echelon form. Well, people could have different echelon forms, okay, depending on their row operations. But if you go all the way and get the matrix in reduced echelon form, everybody's reduced echelon form matrix is going to be the same. Okay, everybody's reduced echelon form is going to be the same. Okay, so are there any questions on that in general? Okay, Nafani's comfortable. All right, well, very good. And then, here in section 1.2, again, they talk about pivots. They talk about pivots, and they go through an example where they go through several examples where they do row operations. And again, this example 3 here, just bring it up here. Example 3, they go through formally the row reduction algorithm. But again, we covered that in our last class when we looked at section 1.1 examples. So I'd like to just move forward here. Move forward, because I want to try to, if I can, give you some time in class to work. Let me just see here. There was something I wanted to mention. Oh yeah. Okay. Your textbook has a lot of numerical notes in them. Okay, and these are very helpful, I think, for everybody, but also who in here is majoring in computer science? Do we have some computer science majors in here? Okay, Abby is, okay. And I'm sure there's some others. Who's minoring in computer science, or who likes computers? Who likes computers in here? I would hope it's more than one. Okay, Andres does. And how many like computer programming? Benjamin minoring in it, maybe. All right, so all right, Christopher, I'm glad to hear that. And Peter does it as a hobby. Well, there's numerical notes in every section of the book. Thank you, Olivia. Numerical notes. So they talk about flops. Okay, so a flop is an arithmetic operation, adding, subtracting, multiplying, dividing on two real floating point numbers. So if you have, for instance, an n by n plus 1 matrix, in other words, if there are n rows and n plus 1 columns, they tell you how many flops are needed to do the reduction algorithm. And this is important because if you have a matrix, say, that's 10,000 by 10,001, 10,000 rows, 10,001 columns, you might be curious how many flops are needed, because the number of flops is going to determine the computing time. And so these kind of issues, they don't come up when you're dealing with smaller matrices, but even with modern computing power, if you have a large matrix and it's like a dense matrix, meaning there's not many zero entries in it. The number of flops is important because that's going to relate to the computing time. And you're going to see a MATLAB, you're going to have a MATLAB assignment that deals with that as well. Yeah, so all right, just want to point a few things out. Sometimes these things get kind of lost, maybe, and I want to make sure you're aware. I mean, this book is a great book. A great book. Okay, now another thing too, existence and uniqueness questions. In example 5, they talk about determine the existence and uniqueness of the solutions to the system, and they give the row reduction here. This, of course, what form is this in example 5? When this row reduced form, for example 5 of the matrix, is this echelon form or reduced echelon form? That's right, very good. That's an echelon form. So getting the matrix in echelon form is enough to tell you what your basic variables are going to be and what your free variables are going to be. Okay, so in this case we had 3 equations with 5 variables. So how many free variables are going to, and I want to say the equations are all different. Okay, meaning you don't have redundant equations in this system. These three equations are different equations. So being that you have 3 different equations and you have 5 variables, how many, when you reduce the system, how many free variables would there have to be? You see here. That's right. Very good, Abby. Very good, Haley. Very good, Nafani. There are going to be 2 free variables. And that means then there are going to be 3 basic variables. Okay, so if you remember the last class, we solved the system and identified free variables and basic variables. If we go up here a little bit, I mean, we'll come back to this, but if we go up to the, this is in example 4, they worked through a matrix. I think it was the exact one that we did, and they came up with this solution set that was like this. Okay, and you ended up with, well, I want to be careful here. I probably need to go up. Probably need to go right to example 4. Here it is, example 4. Let me just see. One moment, class. Example 4. I believe this was the example we did in our last class. Let me just check. One moment. One moment. Yes, example 4 we did at the end of our last class. We had this matrix, and well, they get it. We went from the yeah. This is what we had, exactly this, and we reduced the matrix to, we got it in reduced echelon form. And based on that, look in your notes, based on that, we were able to identify the solution set for the system. And when we identified the solution set, okay, this is the, you know, the 3 equations reduced to those equations that you see there. And based on that, we could identify the solution to the system of equations. And we ended up with 2 free variables and 3 basic variables. Okay, and we did that. And this is what's called, by the way, a parametric description. Okay, your parameters are x4 and x2. Those are your parameters. And the basic variables, x1, x3, and x5, are written in terms of those parameters. Okay, so, and we also know that the number of solutions in this case were infinite. There were an infinite number of solutions because x2 and x4 can be any value you want. Okay, and so you're going to have an infinite number of points with 5 coordinates. But of course, the 5th coordinate always equals 7, right? 5th coordinate is locked in at 7. So given that, all right, in this, I mean, well, now the reason I wanted to review that is because in example 5, this system of equations, it got reduced to what you see here, and you have 3 basic variables and 2 free variables. Okay, 3 basic variables and 2 free variables. And the point that they're trying to make is that if you get the matrix in echelon form, like when they ask in example 5, determine the existence and uniqueness of the solutions, you don't have to get the augmented matrix in reduced echelon form. Oftentimes you can get it in echelon form and be able to answer the question. So we know, for instance, solutions exist. Okay, we know solutions exist here because the existence of the solution is already clear. There's no row that would be like you don't have a row where you have all zeros and then the last number is non-zero. Okay, you don't have, like in the last row, you don't have 0x1 plus 0x2 plus 0x3 plus 0x4 plus 0x5 equals 4. Instead, you have 1 times x5 equals 4. All right, and so the existence of a solution is clear. And also, we know the solution's not unique because you have free variables. So in your homework problems for section 1.2, when they ask about existence and uniqueness of a solution, get it in echelon form and you'll be fine. But then, of course, if you need to find out what the solution is, continue on and get that augmented matrix in reduced echelon form to make your life easy. All right, so are there any questions on that in general for section 1.2? Okay, who's feeling comfortable so far? Maybe a few thumbs up if you're comfortable. All right, thank you, excellent. Well, I'm going to stop the recording here, and let me stop the recording.